All right. So this is 8.5, 8.6 combined lesson. These lessons are both pretty short. And we've talked about some of this stuff already that's in these lessons, so I don't know, I might actually arrange this whole chapter a little bit differently myself if I was writing the textbook, but I guess I've just kind of jumped around a little bit as we've been talking. So some of the stuff we've already taken, so I've combined the two lessons together just into one. All right, so some of the stuff you should know already. We talked about similar shapes, right? So similar shapes or similar figures are two figures or two drawings or two objects even. We're talking about 3D objects today. But if they are similar, that means they have the exact same shape, but they're usually different size, okay? So I have two objects here, and objects are 3D in nature, so you will see similar objects. You'll see that term in the text. And they're talking about like a three-dimensional thing. So all of the corresponding dimensions would be proportional in the same way, all right? So you know about corresponding dimensions as well. I have it written here in the notes. But corresponding dimensions would be the sides that are in the same orientation as the original or whatever. So the height. Wrong pen. Okay, so the height. Let's see. Is it frozen still? Sorry. Frozen still. So the height of this right here, this is h, right? So the corresponding dimension is not this one, okay? It's not this one over here. It's this one, right? Because it's the one that is, that should be h2. So it's the one that corresponds, okay? So they're the same shape, which means the shapes have the same angles. The corresponding angles are identical. The corresponding sides are always proportional in the same way. And this is kind of obvious. We've done this already, but I'm just highlighting. So if you have height, and if you have like width, and if you have length on two 3D objects like this Rubik's Cube you see here, well then the height and the height have the same ratio. Okay, so if you did h2 over h, you would get some ratio. And if you did w2 over w, then you would have the same ratio. And that would also be equal to length 2 over the length 1. Okay, so we're remembering this, right? And this, what's unknown here is called what's it called? Scale factor. Yes, scale factor. Very good. Okay. All right, so 3D objects have all corresponding lengths are proportional in the same way. So if you had a 3D object that was, a little bit longer like this, right? If it was looking like this, and this was part of it, well, then that length would not be proportional in the same way as the other sets are proportional. So they would be not similar, okay? So all of the corresponding dimensions have to check out with the same scale factor. We're good with that? Okay. Now, the objects, yes, are three-dimensional in nature as opposed to just 2D. So a square would be 2D, a cube is 3D. Alrighty? Okay. All right, give me 1 second. Okay, Esmeralda. That's a great name. Feels like that's a name that's like in a Disney story or something. Esmeralda. Oh, actually, Esmeralda was one of the wicked stepsisters in Cinderella, I think, in one of the original ones, Esmeralda. I think, anyways, if I'm remembering my Disney princesses from when I was young. Didn't really invest a lot of time in studying the Disney princesses, but... Sorry?
Anastasia and Gisela.
Oh, it's Anastasia and Giselda? Gisela? That could be true. Was there not a third one, or was this just two in Cinderella? Esmeralda's from Hunchback of Notre Dame. All right, this is very important information. I'm glad we got this on the video. That's for sure. Okay. All right. So I'm a farm kid. I grew up on the farm, so I definitely had some toy John Deere tractors. So I feel a deep connection to this question already. Okay. Anyways, Esmeralda. Okay. Was she good or bad in Hunchback of Notre Dame?
She's like good because he's like new and she's like the only one.
Okay, she's good. Okay, good. Esmeralda bought this toy tractor to give to her younger brother. Isn't that nice? For his birthday. So she's good. In this question, she's good. The dimensions of the toy are given, in the diagram to the right. The scale ratio on the package says 1 to 16. She knows that her brother will want to know the real size of the real tractor. So how can she determine the dimensions of the real tractor? This is almost embarrassingly easy, I think, right? We have 1 to 16. So if this is a toy, the real one is bigger or smaller? The real one's bigger. So the 1 would be the toy, right? And the 16 would be the real tractor. Okay, are we okay with that? So this is toy, this is tractor. Now, it's written in scale and there's no units. Because remember, when you write things in scale this way, you could have different units actually. That could be true. But in this case where there's no units shown, that means they're assumed to be the same units. So if we're given centimeters for the toy, that means that if you multiply each dimension times 16, you'll get the real dimensions of the real tractor in the same units. All right? So height for the real tractor, I'll put H sub R, height for the real, okay, or the full-size tractor, the real tractor, is going to be 12.7 centimeters times what? 16. Okay, someone do that on your calculator? So that's call this the height. This is the width, this is the length. 230.2. Okay, agreed?
203.
Sorry, whoa, 203, not 230? Okay. Slight mix up there with the numbers. Okay, so 203. Okay, everybody else with a calculator, nod in agreement, or shake your head vehemently if incorrect. Good job. What is vehemently? Vehemently means with great vigor and intensity. Yeah. Okay, width of the reel. That's going to be 9.5 centimeters times 16, which is?
152.
152. Point anything?
No.
Just even? Nice. Okay. So what about the length now of the real tractor? That's going to be 19.1 times 16 is?
305.6.
305.6 centimeters. Good. Everyone is in agreement there. Thank you, Jed. That was awesome. Now, this is centimeters, so you would be fine to just say, hey, these are the dimensions of the tractor. Sometimes hundreds and hundreds of things you get a little bit lost with big numbers. So we could easily transform this into meters, which might be a little bit more reasonable for a large scale implement like this. So this 203.2 centimeters is how many meters?
2.032.
Okay, 2.032 meters. Okay, so I have a meter stick here somewhere. Where'd it go? Meter stick. So let's see, this is the height of the tractor. So here's like 1 meter. Here's 2 meters. So the tractor's that high. Now, that's not a very tall tractor. It's not a very tall tractor, I would say. You know, usually being able to touch the top of the tractor is not usually possible. But this could be a small, like, garden type tractor. Okay, so then this one here, 1.52, that's 1.52 meters. Okay, so the width, 1.5. That's pretty narrow. Okay, we're talking about like a smaller acreage type tractor here. Okay, so but hey, that's what the question says. And then 3 meters long, right? 3.056 meters long. So that's a little bit better. Whoa, 3 meters, about 10 feet. So if you look at the tiles on the ground there, those are they're 1 foot by 1 foot. Did you know that? Have I ever told you that? So these are 1 foot by 1 foot, those tiles. So if you count 10 of them, that's approximately 3 meters. So that would be from here to maybe you, Sam, right?
Yeah.
Okay,
No.
in length?
Yeah.
Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
The tile that your pen is
From
on
here-
and this line.
Okay, all right. So yeah, I mean, that's a bit of a small tractor, I would say, but whatever. The question, whoever wrote this question may not really know anything about tractors. Where did my pen go? Did it fall? Oh. Okay, understando? Comprende? Capiche? All right. Well, that's pretty much it for 8.5, I guess. That's all the important stuff there. I think, anyways. So that's kind of all I had planned to touch on for 8.5. So stuff may come up, but let's go to 8.6 now. Here's the 8.6 half. All right. This one we've also touched on just the other day, when we talked about how does the scale factor relate to the ratio of areas. Remember that? So scale factor, recall, so this is a recollection, so we've already learned this, that if you have H2 and H, and these are similar objects, that the ratio of dimensions on similar objects is the scale factor, right? And if they are similar, that means they're the same shape. So guess what? L2 over L1 is also the same ratio, the scale factor, as well as W2 over W1, right? So this is something we've learned, that's what scale factor is. Now for objects, all of the corresponding dimensions have to have the same ratio. Now scale factor for area, okay? Okay, so now this is kind of cool. So think about this. The area is, I'm going to go back to this same diagram up here. Or wait, oh no, I have it down here. Okay, so here's down here. So if I have H times L, okay, and I have H2 times L2, that would be the area of this face, right? So H times L is our area here, and the area of the scale factor of this similar object, this actually is K times H, right? H2 is some scale factor times the original height, and this is K times the original length. Okay, that's what H2 and L2 are. They're the original height times the scale factor, right? And the original length times the scale factor. So guess what? This is actually K squared times H times L. And so that's where we get the ratio of areas. So if you did H2 times L2 divided by H times L, that's the ratio of the areas of the faces. That equals K squared. Okay, now that's writing it just a little bit differently. We did examples, and then we kind of like spotted the connections with the examples there. This is another way of writing that. This is a little bit more of a proof. Okay, this is a little bit more of here's the nature of similar triangles and how dimensions are related with the scale factor. And if we consider area, you see that we have scale factor times scale factor, which is scale factor squared. Okay? So this is just a little bit different way of showing that the areas of similar figures are related by the square of the scale factor. So that leads us now, and you'll see on the right here that I've kind of got a list of different shapes and their volumes, okay? We'll come back to that later, it's in your textbook. But now we're talking about volume, and you guys have already thought about this already, but under the same sort of proof or the same sort of reasoning, take a look at this. Volume 1 is H times L times W. It's 3 dimensions, right? That's how you get the volume, length times width times height, okay? Now, the similar figure over here is the original height times some scale factor, okay? So I actually have K H times K L times K W to get the volume of this larger object. You guys see with me? And similar to the area example I just did, the volume, okay, you actually have K times itself 3 times. So that's actually K cubed times H times L times W. And so here's how the volumes are related. Volume 2 over volume 1 is actually K cubed times HLW divided by HLW. Or the ratio of volumes is related by the cube of the scale factor. All right? Now, I understand that all of that terminology, okay, and the way that I've shown this is maybe a bit foreign to you. Please don't get lost in the weeds here and look at all this and say, oh, I can't do it, math's too hard. Okay? Think about it one step at a time, and I would like you, like I say, we're not doing just examples to draw patterns. I want to move you into that space where you can kind of see, you can trace it along so that you can understand where we're getting to, okay? And some of you, I think, are tracking with me. Some of you may be like, oh, I have to look at this again. I don't really fully grasp it. And that's totally okay. But again, once again, if we're talking about the relationship between one dimension and another dimension in a similar figure, then it's related by k to the power of 1. You see that? If we're talking about an area, that's related by, okay, we're multiplying h times l, so we're multiplying kh times kl. That's related by k squared. And if we're talking about a volume where we multiply all 3 dimensions together, well, we have to multiply all 3 of these dimensions together, which means that the volumes are related by k times k times k, or a k cubed. So whatever that scale factor is, when you cube it, that's the relationship between volume 1 and volume 2. Okay? Question? Yes, k is the scale factor. That's right. So I know in previous lessons I've done SF, okay, but I didn't speak this, but it was on the notes here. So scale factor is also known, because in your textbook you will see k for scale factor. So scale factor is also k, okay? So that's where the k comes from. Yeah. So you don't see SF. I mean, that was just me in the previous lessons, like scale factor, pretty easy, just abbreviated SF. But yeah, usually k or some kind of special constant. But you'll see k in the textbooks there. Yeah, good question. Anything else that you've seen here, guys, that you want to ask about? Please feel free to ask, because sometimes your questions really help other people. So that was a good one. Any other questions? Okay. All right, so we actually don't have to, with this knowledge, if you're given dimensions of an original object, you can find the area of a similar object without actually finding those dimensions on the similar object, right? So you can go straight from area 1 to area 2 now. Volume 1 now to volume 2 now. So this does streamline some of our questions, okay? So one way you can put this, the ratio of volumes of similar objects is k cubed, just like the ratio of dimensions is k, the ratio of areas is k squared, okay? So this is your new information here now. So let's take a look at example 3, and we'll be able to solve this capacity problem, okay? So this is from your textbook. And we'll just go over this, and I'll show you how you can use this to bypass a little bit of work, okay? You can kind of like use the patterns here that you see. So the smaller tank in the photograph, okay, these are special tanks to store oil and different things. So it's a spherical tank. This has a capacity of 1,400 cubic meters, the smaller one, okay? So that is a volume of 1,400 cubic meters, or meters cubed. The larger tank has a capacity, okay? So I'm going to put the smaller one as volume 1. I bet the larger one is volume 2, because those are like the examples we've been doing. So 4,725 cubic meters, okay? So during the refining process, that is the oil refining process, you make oil into all sorts of different things, like fuel and gasoline and plastics and all sorts of, lubricants and different things. Both tanks are filled with oil from a pumping station at the same rate. So the volume here in the tanks are being pumped in at the same rate, okay? Now the bigger tank, which one do you think is going to fill first, a smaller tank or a bigger tank? Okay, probably the smaller tank will fill before the larger tank. That makes sense, right? If you have a small glass and you put it underneath the tap to fill up your, and you turn the tap full on, the small glass is going to fill quicker than the large glass. Amen? Amen, brother. Okay. So we get this. So when it talks about filling at the same rate, we're really comparing the difference in volumes, right? So how long it would take would depend on the volume. A bigger one would take longer. So how many times longer will it take to fill the larger tank than it will to take to fill the smaller tank? Okay. So we're filling these up, and really what they're asking us is what is the ratio of the volumes? How many times bigger is this volume than this volume? Because the fill rate is the same, so how many times bigger is volume 2 than volume 1? Really, I think that's what they're asking. Would you agree? Okay, how many times? So for A, volume 2 divided by volume 1 will give us how many times bigger this tank is. That is how much longer it will take to fill. So that is 4725 divided by 1400. And what do we got there? 3.375. That is awesome. Now the units technically cancel out, right? Meters cubed, meters cubed. So this is just simply a ratio of volumes, okay? That's a ratio of volumes. So that's important for us to remember, okay? That's awesome. So would you be okay to say that it takes 3.375 times as long to fill the bigger one? Does that make sense? Okay, check your textbook there. Okay, because they've got the solutions in there. They might not do it exactly the same way we were doing it, but is that what they come up to? It takes 3.375 times as long?
Yeah.
Are we doing this right? Looks good? Okay, good job. All right, you guys are good doing my calculations today and double checking my work today. I love it. It tells me you're engaged. I appreciate that. All right, so the answer technically is 3.375 times as long. Okay, good. You could times as long. Okay, write that up. Now, B, how many times greater is the radius of the larger tank than the radius of the smaller tank? All right. So we're not talking about volume anymore. We are talking about a single dimension, aren't we? We're talking about the radius. So volumes are related by 3.375. Does that mean that the radii, radius 1 and radius 2, are they related by the same number? No? Okay, so this is a volume, and this is a single dimension. So from what we've learned in this section, how can I use that 3.375 to find out the ratio of the radiuses, or the radii? Any ideas? Okay, cube root. Cube root what? Cube root this number?
Yeah.
Okay, let's go back, and the ratio of volumes is k cubed, isn't it? Now k is our scale factor, so guess what? 3.375 is k cubed. So if I want the ratio of single dimensions, I have to find k, right? The scale factor. So awesome, someone said cubed root, that's awesome. That's really what we're doing here. So k is our scale factor, which will give us the ratio of the two radii. And what is this for a number now?
1.5.
Is it 1.5, just 1.5 even? I think so, yeah, I think that's right. Okay, very good. So that being the scale factor means that the larger radius is not 3.375 times as big, but 1.5 times as large. Okay? Does that make sense to you guys? Does that feel good? Yes, yeah. Okay? What do you think? Does that make sense? Okay? All right, so that's exactly how we do that question. So please just remember, and I'm going to actually add to this little note here. So ratio of dimensions, I think we've written this down before, but is the scale factor, or your K unit there, and then the ratio of areas is K squared. Get it squared there, yeah. And then the ratio of volumes is going to be K cubed. Okay, so single dimensions, dimension times dimension, which is dimension squared, and then dimension times dimension times dimension, if you think about just a simple cube, which is k times k times k. All right. Okay, any questions, or how are we feeling about that? Questions, comments, concerns, queries? Questions, comments, concerns, queries, complaints? Is that what you're saying? Any of those? Yeah. When he gets back, you may. Yeah. All right, let's do the summary, and I'm going to talk to you about just one more little trick that you can use. So the key idea, if two 3D objects are similar, that means that their dimensions are related by a scale factor k, all of their corresponding dimensions. The surface area of two similar objects is related by k squared. The volume of two similar objects is related by k cubed. Okay, so we just went over. If you know the dimensions of a scale diagram, or model of a 3D object, as well as the scale factor used to reduce or enlarge the diagram, that is the scale factor, you can determine the surface area and the volume of the enlarged object without determining its dimensions. So that k cubed gets you from volume to volume. The k squared gets you from area to area. Okay. This is just another way to put this over here, okay, for similar figures. The scale factor is length 2 divided by length 1, or the diagram divided by the original. K squared is the area divided by the area, and k cubed is volume divided by volume. And I will just take a moment to highlight, you may have seen this before, but it's really helpful in science when you have some kind of like simple formula. If you have one thing is equal to a ratio of two other things, just tell me, have you guys seen this before, this little triangle that's split into 3 spaces? Okay, you may or may not like this, I don't know, but in order to solve for any piece of a simple proportion like this, okay, if you arrange things, so here's the first one, you see this, k equals L2 over L1. Now if I wanted to solve for k, all I would do, and let me just, what am I going to do here? Okay, give me a second. I'm going to make a circle here. Okay. And I'm going to do this. I'm going to do pen properties. Come on. Okay, pen properties. Okay, I'm going to make it black. I'm going to make it really big and thick. Okay. All right. So, okay, well, this isn't going to work beautifully. Anyways, I was hoping it was going to be thicker. So if you wanted to solve for k, you cover k up in this little diagram. And then you see you have L2 divided by L1. If you want to solve, if you're given scale factor and length 1 and you want to find length 2, you cover it up on this little diagram and look what happens. You do k times length 1. If you want to solve for length 1, because you're given the scale factor and the diagram, well then you do L2 divided by k. See how it's on top of k? Okay, so that's just one way. You kind of cover up the space that you're solving for. And of course, if this is the cube that we just talked about today, so this is volume 2, volume 1, this would be k cubed, right? If we're looking at this little proportion. So in order to find k cubed, that's volume 2 over volume 1. If you want to find volume 1, that's the original object, and you're given the volume of the diagram or of the scale factored object, then do the volume 2 divided by k cubed and so on. So you just cover up the portion of this little pyramid that you want to solve for, and that's just a way of manipulating the equation, right? So it's a way of solving for each one of these. All right, any questions then about that? Chapter 8.5, 8.6 homework. Right there, and that's your lesson.
That was easy.
All right, you guys as a class have anything to say at the end of this video? Go ahead and say it now.
Love you, Chicken Joe.
Make sure to like and subscribe. See you next time.
Nice. Sounds good.